these smaller Pis, which are Raspberry Pi Zeros, actually 0W, they're Wi-Fi connected. So I'm going to end up with a little network here. Actually, I've got a couple of Pis. I have a basic domestic router, and I have a laptop, a Linux laptop, which will all connect together on a little Wi-Fi network. Human interface devices, basically. So let's go back and think about what our main functions of an operating system are, see what people have suggested for that. So if we have a look at that first widget, definitely loading and running programs is really a prime thing about an operating system. We need to be able to load new programs, run them to make the computer do something useful. Nearly always that means reading and writing the disk. You've got to be able to read at least the program off the disk in order to run it. And generally you're going to be creating results and so on, so you want to be able to write the disk as well. And often it means copying and deleting files around, particularly if you're producing results that you want to copy somewhere, maybe over the network or something, as well as people copying and deleting files. So these are important functions. A couple of people have picked out word processor and web browser. I'd say they're not really essential. These devices, for example, I'm going to be using here, they're not going to end up with a monitor. So why do I need a web browser or a word processor? It wouldn't be appropriate. So those are applications which on a general desktop operating system you definitely would want, but for these purposes you don't need. And in fact, you don't really need a GUI at all. So the installation I'm going to be doing here will have no GUI. So it'll just be a command line version of Linux, which makes the whole thing smaller, fits better on these small devices. So that's what we're aiming at. But bear in mind that copying files and reading and writing the disk are really essential bits of an operating system, which of course makes installing a bit of a problem, because installing basically means setting up a disk full of files, programs and utilities and data and so on, ready to run. So that's actually the operating system, is that collection of files. So we need to copy them onto the disk. And of course, that means you need an operating system to do that copying and to write the disk. So very typically, we need another computer, and I'm going to use this Linux computer here to help me set up the operating systems on the Pis. So if we just have a look at the Pi first of all, Raspberry Pi has, as a disk, actually one of these. It's a little micro SD card, and that fits into this slot here. Got my hand in the way, sorry. So it fits into that slot here, and that effectively forms the disk for this computer. So it's an SD card which contains all the files that make up the operating system. So installing the operating system is really what I've just done, sticking the disk into the computer. And if you're manufacturing a PC, the manufacturer does that job. He prepares the disk outside using another computer and then just plonks it into the machine itself, ready for the first boot. So what I need to do is to take that one out and put it into my computer over here, which I've just realized I've left one in. So I need to just extract the, excuse me a minute, should be slightly better prepared. I've left the card reader inside. This is the magic thing I need, which is an adapter to put this micro SD card inside, so that I can then place it in the laptop. Now I've got sort of muddled over which SD card I was using, but I think the one I've just put in there is the sort that I need, and so that is ready to go. So whichever one, it doesn't really matter. I'm going to start again from fresh. So now I've put it into my laptop, I'm ready to copy the files onto it. Now, I could do that in several different ways. I could sit here and manually copy the files one by one onto it. If I did that, I'd be here for a month of Sundays, because a Linux system contains thousands and thousands of files, all of which need to be put in particular places. It would be a nightmare to do it manually. Fortunately, Linux is a mature operating system where people have built images for many years. The whole process is quite automated, and so I can simply go and pick a distribution and get hold of a complete image of all the files needed for the Linux operating system, and download it and copy them in one chunk onto the SD card that I've got in there. I can actually do that in two ways. I can do it from the command line, and I can do it from a GUI. The command line, of course, would be the hardcore way of doing it. It's quite a complicated command. I need to remember quite a lot of detail. I have to make sure I get it right, because I do run the risk of wiping my own hard disk, which would be slightly disastrous. So I'm actually going to be saying it's the strict alternation, one of each, one of each, one of each. A few people saying it's going to be some of one, some of the other, and a few people suggesting maybe one running maybe to the end, and then the other one has to go to the end. Okay, well, let's have a look. And so I'm going to go back to my command line, and let's see what happens when I press enter. And there we go. You can see some output. You can see the mixture of output coming from the two interleave. And actually what's happening is that one of them is running for a little while and able to produce 50, 100 or so hyphens. And then the preemption occurs, and then the other one gets a chance. And then it gets a chance to do, 50, 100, 200 characters. Preemption happens again, and it's flipping backwards and forwards between the two processes. Now, actually, I've put one of the advantages of writing your own operating system is that you can do debugging and so on. So I've put a debug point in the middle of that program. So that has now happened, and I'm in now a debugger, and I can inspect to see what's going on. So one thing I can do is have a look at the process table. So if I do a capital P, this will show me the process table. So this will show me inside the operating system, the process tables. This is key to what's going on. So this shows the all the processes which are in the system at the moment. And you can see near the top here, I've got process 1. That was one of the ones we created. And that's, you see that it's ready to run. And 2, which is there and also ready to run. What else? We've got somewhere, there we are, down the bottom, preempt. That was the preempt demo. It's been a bit truncated. That is the current process. And so that's the one that's halted at the time that the debug happened. And the other two are ready to, ready to run. There also are some other processes actually in the table which might be worth me just picking out. One is the command line itself. So the command line is there, and that's in a state which is called receive. It's waiting for actually the other processes to finish, and then it'll be ready to run again. There's also the one called idle. And most operating systems have an idle process. It can run if there's nothing else to do. So it simplifies the design by making sure there's always one process that can run. But notice the priority for that is very low. And so that will only run if nothing else will run. There are a few others in here which actually are ghosts. So these aren't, these are processes that have finished. So you can see the commands that I used previously, copy and delete and ls and so on. They've actually finished and are gone, so they're not there, but I've left them in the process table. It helps me with debugging to keep evidence of old processes. So they're just got left behind as a bit of detritus in the process table. So there we go. Some interesting thing is to go back to what the output was actually showing me. This is showing me that Preemption occurs occasionally, enough to let one of the processes run for a little while, and so it is a proper preemptive, a proper multitasking operating system. There's the process table to prove it, and let me just let that process continue until it finishes. So you can see they're back again. Now both processes are finished, and I'm back to the command line, and there we go. Great. So let's just do one more thing and have a look at the inside of that operating system very briefly. I've talked a little bit about the states of current processes, running processes, and so on. And here you can see some of those. You'll see those in the course. Sorry, this has shrunk a little bit for some reason. Let me just make it a bit bigger. It might be easier to read. So you can see the process states, and you can see that there is always one running state which will run until its quantum expires. There may be lots of processes in the ready state which are ready to run, waiting for their turn. Every now and then preemption occurs, we get a rescheduling, and it picks a new one to be running. Processes can be in other states. They can be sent to sleep. They can be blocked while input-output occurs, and so on. So you can see these different states occurring in the operating system. They're all reflected in the process table, and you've seen the states in that process table. But what does that mean in the code for the operating system itself? So I'm going to look at some of the code for that. And this is the code for my operating system. It's written in C. C is a language that you probably will come across at some point. You may or may not have done so far. Details, don't worry about it. But you can see that essentially I have a little routine. This one's called sleep process, that corresponds to every transition in that diagram. So this is the routine that is run to put a process to sleep. So it corresponds to every one of those transitions. I have one process like this. And it's actually quite simple. There's a little bit of error checking code at the beginning, but essentially to change the state of a process to sleep, it's one statement. Set the state of the process to be sleep, make a note of when it should be woken up at some point in the future, and then call reschedule. That's the key thing, to make it reschedule, the operating system reschedule. So that was putting a process to sleep. Waking it up again is resuming a process that's even simpler, actually. It just makes it ready and then calls reschedule. So just 2 lines of code. Essentially, that's all that's needed. If I just jump to the rescheduling itself, that's a little bit more complicated. So this is the key to the of multitasking. It involves the scheduler, and so this is the code for the scheduler in here. And again, it should fit on one page of code, but I've made the font so large it doesn't, but it's only about 25 lines of code. And actually the key part of it is basically what you can see on screen at the moment. So as I say, this is C, so I don't expect you to understand this, but a question, just glancing at that code, can you tell me what sort of scheduler is going on in there? Another widget, can you see, is this a round robin, priority class, deadline scheduler, first come, first served? There are a whole lot of choices. Can you make a guess as to what's going on just by having a look at the code which you can see on screen there at the moment? Being able to glance at code, not knowing the detail, but just have a look at the comments, have a look at the shape of the code is a really useful skill to get. Languages always look different, but actually they have many of the same concepts, whether it's Python, C, C++, or Java, whatever you come across. You will see very similar structures in there. So it's quite useful to be able to skim read code and not worry too much about the details. so as I say, the key part is really what you can see on screen. So let's have a look at see whether people have been able to make a stab at that. It's a bit mean to do that just out of the blue. A lot of people have stumped for priority. A couple of people have suggested round robin. Nobody suggested first come, first served. And you can see that the preemption was allowing the processes to interleave, so definitely not first come, first served. A couple of people have said maybe priority class as well, but a lot of people have have plumped for priority, which is a good answer. So having a look at the code, I think you might have seen the priority choice in here that's asking to see if there's something with a larger priority than the current one. And so it's looking for the largest priority in here. And so indeed, yes, this is a priority scheduler that's looking for the largest priority process and running that in preference to any of the others. So priority is absolutely the right answer. There's a bit of subtlety actually that it does do a circular search of the table. So if the priorities happen to be all the same, then actually it defaults back to being a round robin scheduler. So for when the ready processes are all the same, it does do round robin within equal priority. So actually round robin is actually a good answer as well. So they were both good answers, and well done for spotting that with a new language, with very little preparation. Great. If you'd allow me a few minutes more, just to say that, as I say, that's the core to the scheduler, is simply that loop there. It's only a few lines of code, but of course this is a simple operating system. It's not quite as sophisticated as some. If I do find a new process, the really key thing is I then need a context switch. So the context switch is this mysterious thing that happens when you switch between two running processes, and so that's the other important thing. And I think I've got, not quite there. There we are, there's the code for the context switch. In this system, it's 2 lines of code. It's not that complicated. You save the old context, you load the new context, and the saving and loading is these 2 routines up there. There are a few more lines of code, but not very much. Difficult to see the detail, but essentially what's going on is it's looking for the process registers, program counter, the stack register, the process status register. There's another one, B, and other ones to do with where the stack is, and just save those in a place. When you save the context, and load simply does the reverse, so it just takes them out of there and pushes them back into the processes. This is a little bit simple compared to what you'd see on a full Intel. There are a lot more process registers, and the intricacies of doing it are a little bit more complicated. You expect to see more code than that in a full Intel processor, but it's just more of the same essentially. So hopefully trying to convince you that it's really not that complicated at its heart, honest governor. But I'm going to stop there. So thank you very much for that. I think time to move over to some question and answer, and back to you, Daniel, to run that.
Thanks, John. We've had a really interesting series of questions come in through the chat, so I'll go with the most recent as our first question, as it fits with what you've just been talking about, which is about how you end up setting the priorities on the processes that are running within the OS you've coded.
Okay, well, I can show you that if we can go back to the screen for a minute. I think my demo here, I just very quickly showed you that on screen, that the 2 lines which create the processes are down here, and one of the parameters in there is 3. That's the priority at which those 2 processes are running at, so it's priority 3. So I allow small numbers to control the priority. Priority 0 is for the idle process, the lowest. If it was priority 10, that would be high. Most priorities, processes, I would expect to run at priority 3, so that's kind of an average. So a small number to set the priority, and I do it at the time when the priorities are created. So that's a simple answer for this. Very similar with Linux, except you can have a larger range of priorities and they can be dynamically changed according to the load on the system and so on.
Thanks, John. So stepping back a little bit, we have a very simple question of how long did it take you to write the operating system?
Okay, how long is a bit of string, really? I've been picking away at it for years, but it's a hobby project which I do every now and then. I don't think I've touched it for months, actually, but every now and then I get a week or so and I'll have a little blitz on it and do something new and interesting, hopefully. So I've been working on it for more years than I care to remember. And part of the ambition of doing it was to use these small devices, but also I started it many years ago on a much simpler computer. Yeah, and it has involved writing a new language, which is a bit of a stupid thing to do, but quite an interesting one as well. So yeah, hours of work, days of work, months of work, but elapsed it's been years of work.
I like that you've touched on some of your motivations there as well, because we've had a number of people ask whether you've thought about making it available for other people to trial in some fashion, whether that's through the block materials or just as a general release, I suppose.
Yeah, I did start, it was, as I said, it was a hobby project. And at one point when we were writing this material for the TM129, I did think about using it much more in the teaching material, because it would be really nice to be able to show some of the code actually in the learning. But unfortunately, it comes really in the wrong place in your study. So you haven't yet done enough programming even for this simple thing. And actually, because I'm using the reason I wrote my own language is actually to make the system self-supporting. So although I'm using C, and I've shown you the C code to do it, I can actually make the whole system self-supporting. So the B compiler is actually written in its own language. So you need a bootstrap, for which I've used C, and the runtime system still has to be, some of that has to be written in C, but beyond that, I can make the whole system self-supporting in its own language. One of the motivations for doing this is that in the years gone by, there used to be some very simple C compilers, and they can run on very simple systems. My system is like that, but I've had to fall back to using my own language because the C compilers have all got too complicated for me. And so normally people do it on a hosted system. They write on a powerful system, write the image, and so actually people don't write simple self-supporting systems anymore. So this is a complicated way of saying that it all got too complicated to use in an introductory session, partly because of the mix of languages. You either have to use C, which is itself a little bit complicated for first level, or use my system, which is so esoteric nobody would ever use it again, so it's a little bit of a pointless thing to teach. So I'm stuck on that, and so dropped it.
Good answer. I was also pleased, just thinking on programming languages, I was pleased that your throwaway comment that C++ was better than C didn't lead to some massive discussion in the chat, because a bit of a controversial statement there, but we won't open that can of worms. But sticking with the self-contained element of your question, sorry, of your answer, I was wondering if you could dig into a little bit more of the detail on the VM system that the operating system is working on and what your setup there is, because it's not running natively on the hardware, as I understand.
No, it's not. So the approach I've taken here is actually to emulate everything. So I'm actually emulating the processor as well. So I've got C code, which is emulating a processor, which is not an Intel processor, it's not a real processor at all. That's an approach which actually is quite widely used. So Java uses it. So the Java virtual machine uses what's called a bytecode interpreter. It's essentially the same process. So you think up a very simple processor. It's got one process register, program counter, and so on. Much simpler than real hardware. And that means that you can emulate it all the way through and do things like write what is the equivalent of a hardware breakpoint. So I can do this looking at the inside, looking at the process table in a way that's really quite difficult on hardware. The downside for that is that usually that's a very slow process because you're emulating what the hardware can do. But actually, because it's so simple and because the operating system is very small, actually it all runs in the cache within the processor. So actually it's running at the very fastest rate that the processor can work. So there's a really nice trade-off by working in the software emulated environment, but making it really small. You can put it onto the fastest bit of the hardware and suddenly it runs fast again. So the overall performance I get here, even with a completely emulated processor, is about the equivalent of a Pentium from 8 to 10 years ago. So which doesn't sound that brilliant, but it was good enough 8 to 10 years ago to run Windows on. So, you know, why isn't it good enough now? You know, so there's a kind of an interesting trade-off here in there as well. And just to go back to Java, Java made the same decision years ago to use a bytecode interpreter because it let them run on a whole range of different operating systems. People have done clever stuff with just-in-time compiling on it, so now that really performs really well. Similar approaches taken with JavaScript as well, so there's a good sort of history for that, and people can make it work really efficiently. I haven't, but it's good enough anyway because of this caching approach. It might be worth actually, I did ask one of the questions in the widgets was about how big this operating system is, and that widget actually touches on that. So I wonder if people have answered that and whether we could have a look at the results for how big this operating system is. Okay, yeah, people have plumped for a megabyte or 10 megabytes, and certainly not as big as 100 megabytes or gigabytes or 10 gigabytes. 10 gigabytes will get you Linux, definitely. 1 gigabyte actually would get you Linux. 10, 20, 30 would get you Windows. So we're definitely not in that territory. And actually, the answer is actually less than a megabyte. So the disk image for this is about 250K. So everything that you've seen, operating system, the runtime for the operating system, the command line, the compiler, the utilities, everything fits in a 250K at the moment. So it is really small. And since you've got the actual runtime of it is quite small, and since most hardware processors have caches of at least a megabyte on the die, you're in the fastest possible area of the hardware. So that's shrinking it down actually gets you the fastest speed as well. So there we go.
I mean, it's probably also worth saying that, yes, it may be a Pentium for 8 to 10 years ago, but that is still incredibly useful on a range of embedded systems across the board on all sorts of things. So it is aged tech, but aged tech that's still useful. And I think we touch on some of that later on in the Operating Zoo topic in week 7, week 8, later on in the blog. But operating systems don't just sit on desktop and laptop machines. They sit on all sorts of different things, and Windows and Linux are, sorry, Windows and graphical Linux are not ideal for all circumstances. So a toy example, perhaps, but a toy example demonstrating something really, really interesting. We have got a couple more questions, but we are running further over time than we were anticipating. So I think what we'll do is we'll wrap up here, and the remaining questions I'll send to John later on today, and we'll perhaps deal with those in the forums, if that's okay with you, John.
Yeah, that's fine. Apologies for going over time. Got carried away.
No, there was a lot of interest in seeing the demo, so I think we got the right balance of things there. So I will just say thank you to everyone for tuning in this evening. I hope you found John's demo fascinating. I always do. It is worth reiterating that this has gone beyond the material in the block, but hopefully you've noticed how it connects up in various places. And we look forward, best of luck with the rest of the block and with your TMA, and we look forward to seeing you for the next Labcast for the robotics block, where you'll get to meet, and my name's gone blank on the robot thing. Baxter. Thanks, John. You get to see Baxter, our tame robot. So we look forward to seeing you there. Thank you, and enjoy the rest of your evening.
Thanks. Bye-bye.